81,
Three.
82, something like that.
Two.
82.
Yes.
I've spent a year working with Korean and has been a regular visitor at programs at the Newton Institute ever since. Oh, there we are, you see, it was worth waiting. These extra moments. So he's here for the whole program, which is wonderful. And so here we are, title of this seminar, A Bright Pattern of Flakes in Flow Visualization.
Thank you.
Shigeo.
Thank you very much, the organizer, to give me this opportunity to present a new result of old problem. This is a very old problem, so you may understand. And today's theme is the flow visualization by using reflective flakes. Here I show the three examples. This is a famous one in photo in album. This is a boundary layer turbulence using alumina powders. This is the Taylor-Quet flows using kaleidoscope particle. And this is the visualization using mica flakes. This is what we are using, and I show later in detail. And all the visualization using the flat flakes, flat particle, and this visualization is appropriate for closed flows. Open flow, the particle will go away. So the closed flow is more convenient. If we use dye spread out, but this does not spread. So this is convenient for visualization in closed flows. And there are several problems. And there are two opposite opinions of these flakes. And we sometimes hear this statement that reflective flakes tend to align with the shear layers. And also another one of the advantages of this method is the instantaneous velocity distribution can be captured independently of the history of particle motion. And on the other hand, we have the opposite opinion. What kind of flow structures are visualized? What do these anisotropic particles show exactly? And today, I focus this statement. And so the purpose of the present talk is, well, I questioned this, and we propose a simple flake model to show that the history effects are not negligible, and the flight pattern does not represent the instantaneous velocity distribution. This is our conclusion. And first, model of flake. This is very elementary part. This is like a lecture in student. Sorry, we start from this. We consider the small particle in a viscous fluid. This is particle, solid body. And there are two kinds of force acting this particle. One is surface force, like viscous force. The other one is body force, like gravity or magnetic force. And the equation of motion is Newton's second law. M is the mass of this particle, V is the velocity. And force, the F is the force, is the sum of these two parts. Another equation of motion is this. This is the moment of inertia, and omega is the omega is the angular velocity of this particle. N is torque. And the Brownian effect is included as a random force. I tell this later. And if particle is very small, this term can be neglected. This is proportional to the volume of this particle. This is smaller than surface effect. So we can neglect these terms, and also we can neglect these two. And so equation of motion is very simple. So this is a fundamental one. So the equation of motion is become like this. This is different from the ordinal finite size of motion of finite size of particles. Because the acceleration term drop out. And so this surface force is proportional to velocity difference between particle velocity and fluid velocity. So this lead to this conclusion: the particle move with the local fluid velocity. But on the other hand, the torque, NS, depend on the derivative of the velocity. This has 9 components, and also the angular velocity of particle, and the orientation of particle, and the shape of the particle. So
the particle is very flat.
Here general, not general.
So what is small n?
Small.
Is that just the normal?
Okay. This is for only flat particle. So instead of this orientation of the body. So to describe the motion, we must calculate the force acting the body particle. And analytical expression known for ellipsoid it was derived a long time ago. And but as I know only this case for the analytical expression for of torque and force. If you know other case, please let me. So surprisingly, only this ellipsoid case, the analytical expression is known, and this was discovered long time ago. And this I took the copy from his paper. It's a German, and notation is slightly different. This is force, and G is translational velocity along x-axis. K is viscosity, and this is his result. And this integration is performed over the spheroid. And for torque, the Jeffrey derived in 1922. He considered he assumed the velocity field as linear in coordinate, and derived this LMN, the x and y z component of the torque. And here the coefficient is given by a similar integral as before. So
did Jeffrey know about the work of Overbeck?
I don't. Yeah.
It is?
I don't know, but yeah, maybe. This same notation different, but same, exactly same. But this is for torque, and the other one is a force. And so even the ellipsoid, this difficult integrate appeared. So I think any other bodies give a much more complex expression or impossible.
There's no, so all those terms are viscous related, right?
This is viscous force.
So there's no added mass to
No,
worry
no.
about?
No.
No, no, very slow motion. And I rewrite the Jeffreys equation by our notation, my notation. This ellipsoid, capital letter, it's a coordinate affixed to this ellipsoid velocity field like this. So this is the equation of the motion for orientation of this ellipsoid. And the previous study of the flake motion is based on this ellipsoidal particle model, because only this the shape is known of the expression. And but furthermore, the serious, very serious theoretical study, only these two I found, only these two papers of theoretical study of flake motion. Sabas 1985 and Gaussier 1998. And their conclusion, main conclusion is this particle aligned onto a stream surface. I don't understand very well the stream, what the stream surface is. This is the on this surface the tangential of the streamline, but there are many stream surface can be defined. But this is only two unidirectional flow.
So by thin axis symmetry, you mean one of the semi-major axes is close to zero, the other two are equal?
That's general, not finite.
Is
So
close?
this is not the flat.
Is it like a plate or is it like a rod? Is it oblate or parabolic?
Both included, I think. And this is general. They treated the general triaxial ellipsoid. This is just symmetric, so arbitrary ratio of the axis. But main conclusion here is the particle history neglected. So I oppose this. And this is a photograph of flakes, mica and kaleidoscope. This is far from ellipsoid. And the size is about 10 micrometer, and thickness is below 0.1 micrometer. So these may be characterized by thin particle. And but not necessarily the flat, maybe curved, but main characteristic is very thin. And so the previous model they used was ellipsoid, and our model we use flat plate, but arbitrary shape. This is important, and I explain later. And
Are these plates flexible or rigid?
this is rigid.
Rigid, okay.
And so our model retains this, I think, this is important characteristics: thinness and flat, thin and flat, nearly flat. And equation motion are simpler. I explained it. I explained already. That's simpler. And I explain later, in soon. And deviation from the shape, from the flat, will be considered by random force. Okay, this is new. Very simple conclusion. And the small flat plate, the motion of small flat plate in a viscous fluid is common. That's independent of the shape. It, of course, because it's small, it is advected by local velocity, and orientation changes in the same way as the material surface element, the fluid element. So, proof of this is very simple, but it takes 30 minutes or so. I omit this, but very simple.
A material surface element is infinitesimal, but the plate has...
Infinitesimal.
So how can...
So here we assume small. Small means nearly infinitesimal.
Surface element, you mean some in the center of the plate or some local in the plate?
Yes.
Right.
So
the statement is that you make the surface element rigid, and it does not affect
yes.
the evolution of the orientation.
So the difference is the fluid element stretch its surface area. In average, it increases exponentially. But sorry, this plate does not. So, but orientation is the same, obeys the same equation motion. So this is the equation motion, very simple. N is the normal. Now I assume the flat plate. This shows the normal component of this vector, normal to this plate.
My question is, where do you evaluate that second derivative? At what
because we assume this is small. This is somewhere. The characteristic length of the flow is large.
Yeah, okay, so locally it averages.
Local.
Locally it's fairly constant. So,
Yeah. And this is an equation motion of material surface element. This is written more in most textbook, including bachelor's textbook. This is same with respect to orientation. This no perpendicular. This is perpendicular. So, so this actually shows the time scale of plate rotation is the same as fluid motion itself. So this suggests the history effect not negligible. So plate rotate at the same time scale as fluid motion. So now I show the example by pressing sphere, the flow inside of this sphere. This sphere rotates in around two axes. One is fixed in space. We call this spin axis, omega. This angular velocity of spin rotation. This is precession axis, fixed in the inertial plane. Precession axis. This is rotate rapidly. This is slow rotate. And we define Reynolds number by this. A is the radius of the sphere. U is kinematic viscosity. And typically, we use a radius 10 centimeter, and we use water. And the rotation is about 1 turn one turn in second, so 1 hour. So then Reynolds number become 80,000. And another parameter is the Poincare number, gamma, the ratio of these two. And in our experiment, gamma is 500 times smaller than this, the 0.002. So weak precession. So Reynolds number large, Poincare number small. And this is governing equation. This is Coriolis force, this pressure, including the centrifugal force potential. And this is incompressible. Boundary condition is fixed to the boundary. And we derived an asymptotic solution in this limit. Reynolds number large and Poincare number small, this between these two. And in a region, there is boundary layers, but in a region, in a leading order, the leading order is solid body rotation. We have original solid body rotation by spin motion, but the leading order is another solid body rotation. So that is order, this gamma Reynolds number squared. So by this assumption, this is small. And so the leading order solid body rotation is inclined by small angle from x-axis. X is the spin axis. Z is the precession axis. And second order is this we call conical shear layers. And this is thin layer, and the order of the velocity is like this. This is small but larger than the other part. I use this for theoretical prediction. And this is theta, and this is the small deviation. And so in equation we can write the flow like this. The solid body rotation, this omega is the sum of the spin rotation plus this first order solution. Actually, this was derived before by Busse. This part was derived by Busse. So the axis of solid body rotation was slightly inclined. This is important to create that the flake pattern I show later. And this is also important. This is the second order in the analytical solution, conical shear flows. This parameter, this is 0.06, the order. Now I show the experiment. So here is a sphere. We shoot the light from the top, and we see from the spin axis the pattern on this is apparatus, turntable, 2 meter or something. This sphere, data shot from top. And this I show some last workshop. So this we are looking from positive direction of the spin axis. So rotation, spin rotation, angular velocity 1.5 rps. So this is real time. So after I think 1 minute or so, we see some strange bright pattern like this. This is actually the boundary of the black part is boundary of the sphere. Okay. Stop. Wait. So we after about 100 spins, we see this pattern. So now we consider what makes this strange pattern. First, this is made of 3 concentric circles, roughly. And the radius is like this. And also this is inclined by, there is a fan shape pattern, slight inclined. This is because the solid body rotation slightly from the spin axis.
This is 100 fast spins or slow?
Well, after 100 spins. Yes, the spins.
Yeah.
But this precision rotation is 500 times slower. This pattern was actually found by Banyo and others, but at that time I think they don't know they didn't know the mechanism of this. Actually, this is not so simple like this. And DNS, I think this is the only DNS. I'm not sure, but probably. And why the flake simulation is so heavy? Of course, we must scatter many flake patterns in the flow, like this. But because we must calculate the distribution flake orientation, so we must simulate many particles of different orientation at each point. So consider for this point, we must distribute 1,000 particles. So very heavy, you may expect. So to calculate the distribution of everywhere is impossible. But if we focus only some time instant and some region, some area, it is possible. So that I will show later. This is what I showed before, the equation motion. Equation motion also simpler than before the others. And we focus only this part, on this circle, this part, and some time instant after 100 turns, only that part we focus. So, so we distribute. We choose the inspection point. We distribute points on only YZ plane and track the orbit backward in time for 100 spin times. And after the first simulation, we distribute 1,000 flakes with isotropic orientation at the end of each orbit. And we integrate back or forward the evolution of the orientation. So each flake comes back to the original locations, and we count the number of particles which reflect to the camera, the light to camera. So this can be possible. So this is two typical distribution of the orientation of flakes. This is the nearly isotropic distribution, which is
Normals?
Hmm?
You had one of the normals.
Okay.
This is 1,000
That's
particles.
the normals, though.
This,
The vectors you're representing there are the normals.
yes, this is the orientation flame space. So this is the orientation of single point. But each point we have 1,000 particles with different orientation. So, and the left-hand side, this isotropic distribution is found in a bright location, bright circles, on 3 bright circles. So, because this is isotropic, this is, isotropic, the light reflect in all direction. So we can see the bright pattern, brightness of this position. But the other place, we see almost always we see this kind of pattern. It's flat. So if we are lucky, if we are here, we see that position is bright, but almost other place, this is dark place. Okay. So after calculate the distribution, we count the number of plate particles which normal vector point to this case neighborhood of this direction. Laser come from z direction, and we see from the x direction. So this is the result. The result very surprisingly coincide with experimental DNS. Actually, we were surprised with this result because we used a very simple flat model.
So simple model means the equation for
equation.
the velocity is the fluid velocity and orientation is
like
same as
it's a fluid
surface.
surface. So this I think suggests that model is good, and we also we shoot the light horizon from side, and the pattern becomes like this. It's like 90-degree rotate, but actually slightly different, the pattern, because the solid body rotation inclined slightly. And we also simulate this DNS, so it's also good. And this is the result of DNS, but not experiment pattern like this theory. We calculate a probability density function of orientation of normal vector using analytical solution. This I showed before, the leading order of the velocity field. This is parameter actually we use. Epsilon is important. Epsilon is, we assume that's small. This is the order of this one. Fairly small. This parameter. And this I showed before already. So this is the velocity field across the conical shear layer. If we use this, this x and rho is the x is this spin axis, rho is the radial axis in cylindrical coordinate system. To describe this conical shear layer, we introduce this another coordinate PQ. We have two conical shear from this and two conical shear layers. And this is equation. This is the velocity field for this one. This is complicated. Like this, I believe. And this VP here is W prime. This actually this shape. So I omitted the detail. This is a coordinate, 4 coordinates related with the original ones. Delta is assumed small. Okay. So this analysis is very simple, but actual calculation is it takes very complicated. But idea is simple. We consider the this is this system is the solid rotation flow system. Not x1, x2, x3 is not original precession frame, but as I said, the fluid flow in leading order, solid body rotation, but inclined 11 degree. And here, x1, x2, x3 is the solid body rotation system, flow system. And this is the leading of solid body rotation, and this is the conical shear layers. This is inclined, so the conical shear layer is along to this axis. So I introduced another system, so it's complicated. Velocity gradient tensor of this velocity gradient of this velocity is A prime. This solid body rotation, and order of this epsilon is this is 0.57. I said. And but because the layer is thin, the layer thickness is Reynolds number -1/5, so it becomes gradient is larger, become larger. So now, here the x prime, y prime, z prime is original precession frame, and this red system is the solid body rotation frame flow flake. And because the perturbation is small, the flow is in the leading order is solid body rotation. So it's the orbit particle is nearly circle. So if we now we consider the evolution of the particle orientation on y prime z prime plane, and particle come back in this order in the same position, but orientation changes slightly. So we calculate this difference after one turn by perturbation. And as I said, the orientation of particle is governed by the same equation as the material surface element. It's easier to consider the material surface element, because if we write the equation of n, we add some terms. But if we know the solution of this equation, just normalization gives this solution. So we consider now this equation. This is simple, but if we further make, this is tau is the straight time because we consider only the evolution on that surface. Okay. But if we further rotate the system from red to green, this angle, equation becomes much more simple. Only this term is non-zero. And so here we have two constants, A and B. A and B is actually this part was very complicated to calculate, but actually it's written like this. The velocity field in the conical shear layer gives this A and B. And if we introduce this angular angle of this orientation vector, the equation becomes like this. The solution of this is simple, like this. So if A and B is 0, both theta and phi are constant. And initial condition is isotropic because there is Brownian motion. Brownian motion time scale is about 1 minute or 2 minutes. So we always start from isotropic case. So if the position of A and B, both A and B vanishes, that part is always isotropic, remains. And this is spatial distribution of this function on that plane on circle. It is not there we have 3 minimum, 4 minimum. But this is not exactly 0, but I think this because the asymptotic solution, we take on the leading order of the solution. But if we take this threshold, this value, this is the minimum position, and this is also so very similar. And if we know the evolution of theta and phi, we can calculate the probability distribution function p, This is the exact relation. If we know the evolution of theta and phi, this comes from the conservation of probability. But now we add the diffusion term because there are two effects: orientation diffusion, either Brownian motion or deviation from the flat shape of flakes. Flakes are not necessarily flat, as I said. And this sigma, this coefficient is this D is diffusion coefficient, and at the present case, epsilon omega is like this. So this is about 0.3 D. And the diffusion coefficient of Brownian motion is known. There's two diffusion coefficients. One is diffusion of position of particle, and the other one is diffusion of orientation, the effect of Brownian motion to the orientation. And this, many people know this. Some people know both. And the typical length scale, the size of the particle is micrometer. And then, so particle diffusion coefficient is very small. On the other hand, the diffusion coefficient of for orientation is small, but of order of 20 or some minutes, 30 minutes or so. So this may affect. So this case, the Brownian effect is like this, 0.02 or something, depending on the size of the flake. And so because we know the equation motion of theta and phi, that the equation for PDF is written like this. That we solved this. We found the steady solution of this, and that this is the result. Depending on the coefficient, diffusion coefficient, this is the axis. The theta is the radial axis, and the phi is this is the orientation space. So if diffusion coefficient becomes small, it shrink to point. Okay, so this is 0.02 or 0.02. And so now we calculate, because we found that steady solution. Now we can calculate the where is bright, where is dark, by calculating the angle, the distribution, value of distribution of some angle. So this is the result. Depending on this coefficient, the shape changes slightly. Of course, the diffusion coefficient is smaller. The bright region is sharp. If diffusion is stronger, this is wide. And we compare this with the experiment, which is closer. So we chose this one. This is close. This is more. So we chose this 0.01. So this is. But this theory the result is closed for these three circles, but there is a difference in fan-shaped region here. There no in the theory.
Your theory is incorporating the conical shear layers,
This come from conical shear layer.
but, right, so,
Uh,
okay.
But that's a leading order. We must consider next to the leading of the second or third order. We must consider, I think. So this is the experiment comparison of these three. Now, we checked we compared the theory and DNS in the central region. So there is a difference between this is our conical shear layer gives this distribution near center. This comes from DNS. So these terms circled is missing here. So we calculate the bright pattern using only these terms. Then we get this. So this shows this agrees with each other. So we think from this result, we think we must take the next order to reproduce this part. And now, lastly, we consider visualization of turbulent flow using flake. And this is from my old paper. In isotropic turbulence, this is very low, Reynolds number low. Isotropic turbulence, we have as the smallest vortices, we have this kind of vortex tube-like structure. The length scale is like Kolmogorov scale, and velocity scale, Kolmogorov velocity scale. This is well known. And this is the comparison between flake visualization and DNS. Entropy is a vorticity squared. And important point is this flake visualization was obtained, averaged over 8 Kolmogorov times. This is important. And actually, that vortices rotate with other Kolmogorov times. So after 8 Kolmogorov times, the elementary vortices rotate. So we can see the bright, that flakes has some probability which reflect the light from us. So this is quite similar, but if this average, we take instantaneous pattern, we want to see the instantaneous, this is much different. So this is important to see the small scale. The conclusion, we have now we have three conclusions. First, the flakes can be modeled by small flat plate plus random noise. Second, the history effect non-negligible because time scale is like this. And the bright pattern does not represent the instantaneous velocity field. So now I think I understand a little bit about the flow visualization. Thank you.
Well, excellent, thank you. Any comments?
So in liquid crystals, often pneumatics and trying to do, they're like little worm-like little rods.
That's
Sometimes-
different.
Sometimes with a little bit of right, a little helicity or a little virality. So are there models like yours for the rod-like or even little helix-like particles that not only models but also do people use those for visualization?
But for rod, I think we must find another completely different.
There was some work done on the rod-like particles.
Yes.
The low Reynolds number flowed by Tillett back in the early 70s, following on the same period as mentioned Leal and Batchelor was working on these things. So there is an asymptotic theory for needle-shaped particles in Stokes flow, and the force, and I suppose the torque. Maybe the torque in that case is very small. It's not like much smaller than for a plate.
So that's more difficult because the flat plate case, inertial force negligible. But
I think it was negligible too for the.
that surface, no surface. Negligible.
The purpose was to consider, for example, sedimentation of a suspension of needle-shaped particles. So they so they were subjected to a force, and the problem was to find out how they rotated and moved under a force. Now yours is rather different. Your flakes are not subjected to any force because you neglect their the body force, which is the weight.
So.
Which is
Since rod case, I'm not sure. I not neglect to the body force. Yes.
Yeah. Well, I don't think so. That because that's, as I say, it was sedimentation.
A single sedimenting needle
Yes.
just retains its orientation.
That's right, and it sort of
So the tail
goes
is
down
moving,
at a particular angle. Yes. Tony.
So, early on, you talked about taking 1,000 orientations and finding out
each point.
At each point.
Each point. Each
But-
point 1,000.
What if you had a fluid element and you wanted to know how a little fluid surface moved, you would just compute the strain tensor, and that would give you all the information that you need. But maybe you're doing not quite that. You know, the strain tensor, is a 3x3 thing that would save you a lot of work.
But you have to push it forward along the trajectory. Which is what he's doing.
Yeah.
But if he's doing them all independently instead of doing a variation
Yeah,
equation.
but this strain tensor does everything independently too. I mean, it has all the information you need.
3 or 9? 3.
That covers a fluid element, a material
It's for a fluid
element.
element.
But somehow the particle, this flake, is not
It's not quite that.
not quite a fluid element. It's
Okay.
rotating at a different rate. This is the point you're making.
Yeah, the same.
He says it's
The same.
Rotates.
So yes.
Maybe
Maybe
we
3.
can,
Yes, 9.
maybe we can talk about that.
Yes. We can save.
If it is the same as a fluid element,
Yeah, same. Yes.
then it really should be. Why do you, then it's
Yeah,
hard to know why you
yes,
need it
yes.
at
We can
first.
save. Yeah.
Okay.
So,
That's Stuart.
so I suppose somewhat related question. Firstly, I thought you were telling us, which is something that I myself sort of thought of it, but never wrote up years ago, but that if this is your flake, what you're seeing is sort of random grounding motion is just tilting it. So if you've got simply the shear, then flips
Yeah,
over
yeah,
periodically like that. So yes, it spends most of its time approximately aligned.
Yes.
And so that of course is missing from just looking at the strain rate tensor, sort of that element of it.
Yeah.
Unless you bring in a subsidiary model for sort of the
But that
orientation.
case only unidirectional
Yes,
flow we
but
can.
what I was also going to say is, of course, other elements of the strain rate tensor are also important. If you consider simple strain, for example, if you've got simple strain like that, then your particle is going to end up with a steady orientation. It's not going to be flipping over like it's got the steady orientation will be like that. Of course, in the example that you showed us most about, it was shear dominated, and so there wasn't an element of that. But in the case of a turbulent flow, then both components are, both behaviours are playing a role. And so, I suppose, sort of as an experimentalist who's used these sorts of visualisations many times and thought about it a lot, what I would really like to have is a good answer for what it is we see in turbulence. You showed us sort of the relationship with the entropy, and again, that is something which unfortunately we haven't published, but we've also seen, but it's not the full story.
I don't think there's no direct correspondence. I think the people compares many quantities, and sometimes that's very similar, but that not but not exactly. So, but before we thought this pattern is correspond to some flow structure, but actually not. So we must be careful.
Well, I'm just thinking out loud more than a question. The issue about whether the platelet is like a fluid element. I guess one would be thinking, are the eigenvectors of the strain matrix and the eigenvectors of the inertia tensor, the platelet, essentially aligned or not?
The inertia plays no part.
Oh, no inertial effect. So this is.
Well, it's just responding instantaneously to the surface stress.
No, not instantaneous. That.
Oh, you said not instantaneous.
No. That.
Well, if it's not instantaneous,
instantaneous related is the time derivative of the orientation and the rate of strain tensor. This is instantaneous, but so.
It takes a while to flip over.
Yeah.
So
it takes a little while. There's a little delay, time delay in responding to the local
not little, not little. That's that's the same order of the flow. That's the point.
Actually, that would be nice, just to take a model flow and one particle and to demonstrate this effect.
I think many people did.
Is there anything you can say if the flow is somehow constrained to be two-dimensional? So that's, for instance, I'm interested in turbulence, in two-dimensional turbulence.
2D turbulence.
Yes. How would the flakes behave?
Same thing. Either 2D, 3D. I see.
But don't they always reflect? I mean, if they're two-dimensional, they're constrained to two-dimensional.
This way, not perpendicular, but.
You're putting them in like this.
2D means the flow is not dependent on z direction. So you consider this?
Yes.
I don't know, but.
Would the three-dimensional orientation of the flakes be constrained to the 2D? And I think the answer is probably not.
By the fifth, it's not very interesting. So what, this is an elementary question, but your last slide said they do not show something. What actually do they show? Do you have an answer?
Actually, that's an integral effect. So no answer. No direct relation. We must be careful to say very easily something.
Does they show something?
Take a suitable time average.
Time.
In the
like
turbulence case, it was a question of time, wasn't it?
It's like a probability distribution that's been pushed forward on average.
but as I showed, only smallest scales may be visualized, because that's in turbulence case, the Kolmogorov eddy rotate quickly.
That's one of the big problems, is that your highest your highest vorticities are at your Kolmogorov scale end of things, but what you clearly see in a turbulent flow is something which is got a much larger scale. You can see things which seem to be of your
the boundary between turbulent and laminar, there is activity, high activity, so you can see.
Maybe we continue this discussion over lunch, but can I just remind you that this week is a little unusual. We have a seminar tomorrow.